Today's speaker is Yannic Steenebeck with the talk Approximation of Coalescing Diffusion Flows. Please, Yannic.
Hello, thank you for letting me speak here. I will talk on approximation of coalescing diffusion flows and will first define what coalescing diffusion flows in my case even are. First a few reminders. This talk is based on my master's thesis and it was supervised by Yannic Steenebeck. So I have to thank her for all the caring and good supervision. And another thanks goes out to Andrei Dorogovtsev and Irina Nishenka because my work is heavily based on their work. And probably all results I will state here are given for a sigma which is 1 and a sigma which will be nice in my case. So the two papers I listed here are my main source of inspiration. So yeah, it's not all my ideas. So first, what do we have to understand under coalescing diffusion flows? In my case, it's a little bit maybe different than other constructions of coalescing diffusion flows because I don't really talk about flows. So there's just one time variable. So we don't have to look for co-cycle properties or anything like that. But I want the most regularity in an analysis sense. So let's talk about my definition. So a coalescing diffusion flow with diffusion coefficient sigma, where sigma is a function from R to R, is a random element of this space dRCRR+, and the D is the Skorokhod space of RCLL functions. So in this case, RCLL functions from R to continuous functions on R+. So we can interpret it like that. For every point on the real line, we have a path on with time greater than 0. So and this random element has the following property. First, it has a martingale property. So the one-point motions, when we fix a point in space, these are continuous and square integrable martingales, and they are martingales with right to the joint filtration. So joint in the space variable. And further, it has good starting points in the sense that the one-point motion associated with the point U is starting at the point U. And third, there are no crossings. So the random maps, when we fix the time variable, are non-decreasing. So the paths started at different U's don't cross. Maybe they will touch each other, but they will not go through each other. So, and the fourth point, which somehow fixes the distribution really, is that we prescribe specific quadratic covariations for these martingales. So they are square integrable martingales, so they have covariations. And these covariations are given by this formula, which I didn't wrote what the tau is, but the tau is the first time the one-point motions x from starting from U1 and starting from U2 cross each other or touch each other. So this integral is 0 unless they if they haven't touched, and from the point they touch each other, it's essentially the quadratic covariation of a particle with diffusion coefficient sigma. So, and you already see in this formula that there's only appearing the U1 or symmetrically it could be U2. So we hope that they really are one particle starting from the point where they touch, from the time point when they touch. And this really is the interpretation of this definition. So it's a system of particles that are each started at a point of the real line, and they behave like independent solutions of the one-dimensional SDE, which has a diffusion coefficient sigma and static point at U, at least until they meet. And after their meeting, they should move together as one particle, which still obeys the SDE. So, and because this is such a long definition with many properties, it's maybe not obvious that such a thing even exists and has a unique distribution. So yeah, let's talk about that. But first, I have to remark, if we set sigma gleich 1, so if sigma is the constant 1 function, then we just obtain the ratio flow, where the one-point motions are just Brownian motions. So, but let's talk about the theorems on existence and uniqueness. For this, I will assume that sigma is a bounded and Lipschitz continuous function. Yeah, there are many reasons for that, but a first reason why sigma has to be this nice, at least for my proofs, is that the SDE isn't well posed in many non-Lipschian cases, and the boundedness, yeah, it's just easier with this. But some boundedness has to be there. So the first theorem is that actually when such a sigma CDF or two such sigma CDFs exists, then their induced probability measures, their distributions are unique. And the second theorem is that there actually is a sigma CDF with this type of regularity I prescribed in the definition. Yeah, so probably easy to understand the statements. And now let's talk a little bit about the proof strategies of both of these theorems. And for the uniqueness, the key idea is that the L-point motions of such a CDF are actually, at least in law, just coalescing solutions of the SDE we already talked about. So the trick appearing here is now that we have to add in independent solutions of this SDE every time two one-point motions coalesce. So we will get actually, at least in law, a solution of this L-dimensional SDE or independent solutions of this one-dimensional SDE. And yeah, of course, we first just have that the quadratic covariations are like the solution, like such a solution would have. But yeah, the bridge between these two properties is just the Levy characterization of Brownian motion, or an argument that heavily relies on that. So now that we have that, we can just say, okay, we now just we know the unique distribution of the extended process where we added in the independent solutions, but the original L-point motions are measurable functions of our extended process, so their law is also uniquely determined. So that settles the uniqueness of the definition. And the proof strategy is, yeah, a little bit like, if you know the paper, I don't know how famous it is or anything, but there is a paper on the modified massive erasure flow by Konodowski and von Renesse. And yeah, my construction is very similar to their construction. And the basic idea is just to discretize the space variable and then construct a sequence of processes which will converge in distribution to a sigma CDF. And these processes just live on a grid of size 1 over n, or anything that goes to 0 with n. And they are just the endpoint motions that we imagine the sigma CDF to have. And everything between these points will be more or less constant. I will write this down formally on the next slide. And in particular, this existence proof is also an approximation result, because the argument really shows that we can discretize the space variable and approximate a sigma CDF in this way. So it's not only existence in an abstract way, but in an approximation way too. So let's discuss this discretization. First, we have to talk about why these endpoint motions actually exist. And this formulated in this lemma. So there's always a probability space that supports a sequence of stochastic processes with the discretization size n, and this will be the endpoint motions which start at k over n and have the properties we imagine the endpoint motions to have. In particular, these are also continuous square integrable martingales without their joint filtration, and they have the quadratic covariation they should have. So, and out of these building blocks, we can now actually define random functions on the whole real line, which gives path for every starting point by just setting these xn.
Excuse me, Yannick, can we just go back to the previous slide?
Yeah, sure.
Okay. How do you prove the existence of this sequence of the processes, ZKN?
Yeah, it's actually just the uniqueness in reverse. So we use solutions of this STE, and then identify the particles when they coalesce, and just do that in an ordered manner. So we have a coalescence scheme.
Okay, so you can start from arbitrary finite number of points. Am I right?
Yes.
Then can we just check that due to this uniqueness, we get the consistent family of distributions related to this finite families of points?
Yeah, probably, but this unless I'm false, this won't show that the limit will also be with this regularity.
Okay,
so we have to show tightness
you don't want to use Kolmogorov theorem, and after this pay attention to existence of the good modification. You just want to get this modification already. Okay, thank you.
Yeah, that's probably another approach how one could do it, by first using the Kolmogorov existence theorem, and then some type of Kolmogorov continuity theorem on the space would probably work also, but I don't think it would make that much of a difference. Because one would probably show more or less the same things that one have to show when one wants to get tightness. So out of these building blocks, we now build random functions on all of the real line by just setting them constantly between this starting points. And now the theorem from above, or indicated from above, is formulated in formally just that these xn actually converge to a random variable with this type of regularity, and which also is a sigma CDF in my definition. So, and the whole proof is somewhat technical because, yeah, tightness in this Goldilocks space is not as easy as in, yeah, well-known examples in, for example, just the continuous functions. So one has to do some estimates that aren't as straightforward as typically. And then we have to show, identify the limit. And in particular, we have to show the martingale property and that the covariations are right. Yeah, that's all doable, but yeah, there is some technicality involved. So that will at least settle the existence for the slides. If you want to note in more detail, please feel free to email me, and I will send the master's thesis to you.
Maybe it will be good to say just few words how the criteria of tightness in this space DRCR plus looks like. Where you face a new problem comparatively to usual case of space of continuous function, and what was the key idea to overcome this difficulty?
So the tightness criterion itself is works with like two conditions. So first, you have to show that these xn are tight if you fix a u, so fix a starting point. So this is not as hard because these are elements of the continuous functions, and you can use the usual Kolmogorov tightness criterion, where you estimate differences or get some Hölder type, stochastic Hölder type of property. And this is easy because these are nice martingales and they have good covariations. So you can use Burkholder-Visconti or things like that. And but the second part is now that you also have to get estimates which are somewhat uniform in the U, and in particular they have to be two-sided, because the limit function will have, at least for some sigma, jumps. So what you have to control is not like xn u plus h minus xn u, but also you have to control one of the sides. So
okay, it is reasonable, but let me ask you, these functions which you construct and the function which you want to have in the limit are non-decreasing. The specific, this is specific part of Skorokhod space. Is it much more easy to work with it, or it is exactly the same as in the old Skorokhod space?
Yeah, so I don't know if it's really important for the tightness part right now, but obviously in later parts it will be heavily used that these functions are decreasing, and you have always have this order. So yeah,
okay.
that's
okay. Yeah. Thank you.
Okay.
May also I ask a short question?
Yeah, sure.
I have a question regarding the identification of the limit. As I remember, when we prove that the limiting family of processes in the modified massive variety of flows satisfy the martingale problem, we had to show that some kind of the continuity of the the meeting time, of the time it seems sigma, you denote it. And in that case, we overcome that problem by the fact that the diffusion or the difference of diffusion was bounded below, and then we had this continuity. But here it seems that you don't make any assumptions on sigma, and it could be also somewhere equal to 0. So doesn't it make any additional problems?
No, in this, I also noted that when I saw this proof, and it first confused me. But actually, it's in this situation you don't need that, because you don't even have to show that the stopping times converge. Actually, that's a feature of. I think that's a feature of the somewhat easy covariations in this case, opposed to your case, because you just have to show that that the covariations are 0 before they meet, and you don't actually have to show the convergence of the stopping times for that. But the argument is a little bit technical, but I would be happy to email you the section for that if you want to.
Yes, it would be interesting to see details. Okay, thank you.
Okay, no problem.
Can you ask you? I'm sorry. Can you ask you to email to me too?
Yeah. Can you please write it in the chat, because
I will.
I can't see who even asked.
Yeah, I will. Thank you.
Okay, thank you. Okay. So I will now proceed to other approximation results than the one needed for the construction. And the first approximation is an approximation by non-coalescing diffusion flows, which is inspired by the work of Dr. Götze. And for that, we now consider sigma with a little bit more regularity. In particular, it has to be bounded and with bounded first and second derivatives. And we have a test function phi. And now we consider a stochastic differential equation with right to the Wiener sheet. So space-time white noise, if you want. And it reads like this here. So we start at every point u, and then dx epsilon is just this integral in time. So in space, I'm sorry, where we apply sigma to x epsilon, and then have this factor phi epsilon x epsilon minus p. And the phi epsilon is just the rescaled version of phi, so that the L2 norm stays the same for epsilon, goes to 0. But of course, this will converge to the Dirac distribution in some sense. So these are the non-coalescing flows we will consider, and these should converge in some sense, which I will clarify, to the sigma coalescent diffusion flow. And first we have to note that now if we want to discuss approximation in this sense, these kind of guys all have continuous paths, but our sigma coalescent diffusion flow not path, sorry, maps. So if you fix the time, say t equals 1, then these maps are continuous also. But in the case of a coalescent diffusion flow, these maps could be heavily discontinuous in the sense that they are jumps. So we have to be a little bit aware of the topology. And in this case, we will use the Skorokhod M1 metric, which isn't as well known as the J1 metric. So the J1 metric is the one that is usually used, but yeah, because as I already said, we want to approximate functions which potentially, so for some sigma, have jumps by continuous functions. And this isn't allowed by the J1 topology because the limit of continuous functions in the J1 topology is again a continuous function. Yeah, if you don't know the Skorokhod M1 metric, I will explain it very shortly. So to each RCLL function, you can associate a completed graph. So you just connect the jumps actually. And the AM1 metric now measures how far apart the nearest possible parametric representations of these completed graphs are. And in particular, this accounts for the possibility of jumps in the limit. So the corresponding theorem now is that if you fix the time, say 1 for simplicity, but this isn't important at all, the values of x epsilon at this time will converge to the values of sigma coalescent diffusion flows in distribution on the Skorokhod space equipped with the M1 topology or M1 metric. And as this topology isn't as easy to understand in or the convergence in distribution, we make a further reduction of this. And maybe not so obviously, but by the continuous mapping theorem, the convergence of these random functions we want to obtain in the M1 topology is roughly equivalent to the convergence of random measures in Wasserstein space, and the random measures I mean here are just the normalized mass distributions of x epsilon and x. So, or to say it more technically in this sense, they are push forward maps of the Lebesgue measure on the interval from A to B, if we consider x and epsilon as random maps yeah, from these intervals.
And which Wasserstein topology you consider here? Because we know that there could be different powers in the Wasserstein metric.
Yeah, I just mean the Wasserstein metric, which is equivalent to weak convergence.
Ah, okay, 0. Okay, thank you.
So this suffices in this case. Yeah. So yeah, and maybe I will shortly explain why these two convergences are roughly equivalent. So this is more or less in analogy to the fact that convergence of probability measures is the same as convergence of their distribution functions at each point of continuity. So as I said, these functions aren't really continuous in the limit functions aren't really continuous. So that could be a problem, but yeah, the jump points aren't fixed. And in particular, if we fix a point, there will be a jump at this point with probability 0. So that's why I said roughly equivalent. We can make it work in a stochastic setting.
Maybe there exists such a Levy-Prokhorov distance between the distribution functions, where we allow these functions to move in the coordinate by epsilon and also in the space by epsilon. Yeah. So it is closely related to this thing, I think, because you already said this M1, where you do different parameterization to account the jumps. So maybe this can be an explanation why it is related to the weak convergence and then to the convergence in Wasserstein space. Yeah.
Yep. So, and yeah, because of this at least rough equivalence, we'll now just focus on the convergence of this induced random measures. And so it will again follow just by tightness and identification of the limit points. And in this case, the tightness is easy and much more easy to understand than tightness in Skorokhod space itself, at least for me, because yeah, here we just have uniformly bounded expected moments of these guys, and so yeah, they lie with high probability in pre-compact sets in the Wasserstein space, so they are tight. And the key argument in the identification of the limit point is the following. If we fix a bounded and Lipschitz phi and evaluate the integral or its kth moment against the random measure nu, then that's the same as the right-hand side of this formula. And this right-hand side of the formula is actually determined by the distribution of a possible limit point of yeah, the L point, or in this case K point motions of x epsilon. And yeah, okay, why does this suffice? So that's yeah, the left-hand side determines the distribution of a random measure in Wasserstein space. So and using this formula now, so we see it suffices to identify the limit for the K point motions actually. And yeah, how do we do this? Again, tightness and identification of limit points. Tightness is once again rather easy because we have the Kolmogorov tightness criterion where we have to calculate that yeah, stochastic Hölder type of property holds, and this is easy once again in this case because we have all moments and the Burkholder-Davis-Gundy inequality holds for the martingale processes. So it's easy to calculate and or estimate. And yeah, once again, identification of the limit points is a little less straightforward. It's similar to the difficulty is similar to the difficulty we already encountered in identifying the limit point of the space discretization for the existence, because we once again have to show the martingale property for the limit, and most importantly that we have the right covariations which play nicely together with stopping times. And in this case, it is of help that we have this Skorokhod representation theorem, just to say a little bit on the technique. Yeah.
Maybe
okay,
maybe here you have to check some properties of the meeting times which Vitaly Konorovsky asked before.
Yeah, it's actually the same problem, but once again, in this one doesn't have to show it in this case. Actually, one doesn't have to show convergence of stopping times or anything. So yeah.
But you still need to show that covariances are convergent.
Yeah.
And
sure,
they're not continuous functions. Those functions that are integrated, they are not continuous. So something should be done.
Yeah, sure, you are right. So there, maybe I can say a little bit about the trick I use. So I don't know if I should call it a trick, but yeah, maybe it's a trick. You first can simplify the problem a little bit if you also assume that the covariations do converge. and you can show once again by a tightness argument that the processes and their joint covariations converge together, and then you can use the Skorokhod representation theorem on these type of things to show that the covariation has to be 0 at least before the stopping time, because you don't know that the stopping times converge or anything, but as I remember, no, I don't want to talk nonsense, but they are not continuous, but there is a relation which allows one to obtain that the quadratic covariations are 0 at least until the stopping time, and then you can conclude how the stopping time has to look after that, because when the quadratic covariation gets to 0, the martingales have to be equal from this point of time 1. So that's just a reformulation actually of the fact that continuous positive martingale stays at 0 from the point on it hits 0, and the positivity in this case comes from the fact that we have this non-crossing. So the difference of 2 one-point motions is positive if you write the difference in the right order. I don't know if
it's not entirely held, because there are still some technical details here, because if you want to prove that something is 0 before they meet, I think something like the Fatou lemma might help, but it's not necessarily gives you the equality for the stop meeting time, but for the limits of meeting times for previous, which doesn't exist. So yeah, I think it. Yeah, that's why I asked for the thesis, because it's those details are interesting for me. I think.
So yeah, I think first I think you are right that one has to be careful at this point, and I noted that in your proof that you had to show convergence of the stopping times, and for this it had to be some non-degenerate sigma has to be there. But I will send you the section, and you can say if you think that's right or not. But I think in my case it's just easier as in your case, and you can actually do all this without showing convergence of stopping times.
Thank you, but I'm not Vitaly, I'm the other guy.
Oh, sorry.
Okay, may then I just add here? Yes, I completely agree with you that in your case it is much simpler, because in our case we had to care what is after the coalescing. We wanted to know that it is inversely proportional to the mass and so on. But still, as I understand here, you need to know at least that two processes after the meeting coalesce probably to make that conclusion. And maybe you indeed use that fact in order to get the precise form of what happens after the meeting. But also, as I understood, a few times you already mentioned that processes either can meet or coalesce or touch each other. So therefore, as I understand, on the other hand side, you don't work with a modification which of the processes which coalesce. So therefore, here I worry a little bit whether you take that into account.
You actually might need to add into the definition.
No. When you pass to the limit, you need to additionally show, because the space of all paths which coalesce, it is not closed subspace. Therefore, you need to prove that.
I understand. I had the same problem years ago.
Okay, thank you.
I understand. Thank you.
Yeah. So you think there could be the case that the paths touch, but
you see, maybe I try to explain.
but stray apart after that, without.
Suppose that your
crossing each other.
wait a moment, just suppose that your prelimit paths get closer and closer, but they never meet, right? They cannot meet. But so it may look like the limit point touch, but then split.
But he already said the limit point is martingale, which is non-negative. So
But to prove that it's a martingale, we need to prove something about covariances.
yes, and
It's like a closed circle.
Yes, it was said that we already have some hypotheses about covariance. Firstly,
Yes, but I still don't see how this works.
So you first show that these actually are square integrable martingales. Then the difference of two one-point motions in the right order has to be a non-negative martingale. And a non-negative continuous martingale.
Yes. I understand this argument. I just don't understand. So how you get that the difference is a martingale, it's a limit. If you do not know
a weak limit of any martingale.
The weak limit of martingale
is again martingale. So here is no problem, and I believe that it is here.
Okay, yes, this works. Thank you.
Okay, let's go first.
Okay. Yeah, that on the proof strategy, and yeah, I will happily send the critical or any section to you. So now let's talk about approximations by a different scheme. So first we have to define what a different scheme in this sense mean, and it's an analogy to the Euler-Maruyama scheme for STEs, and the whole idea is based on the ideas of Irina Nishenka's paper. She has done all of this for sigma equals 1. So what we first do is consider a sequence epsilon n of positive real numbers which converge to 0. So this will correspond to the rescalings in the SDEs we saw. And we construct the following difference scheme. So at every point u and at time 0, we will start at 0, just like the CDF does. And now at every time step, we will add in noise which is dependent on the position where we already are. And the noise comes from a sequence of independent centered Gaussian processes on R, which have the specific covariance which stands here. Okay, this is the construction of the difference scheme. And now the theorem for that. So when we assume that the sequence epsilon n converges to 0 slowly enough, which will I explain later more explicitly, then the difference scheme at the last discrete time point converges to the values of the sigma CDF at time 1. So how does this go? First, we have to connect this discrete time difference scheme to the discrete time approximation of non-coalescing diffusion flows we saw earlier. So yeah, this is the SDE we saw earlier, just not rescaled in this case. Yeah, but yeah, there should be a phi, not a phi epsilon in this case. But yeah, it's just the non-rescaled version of this, but yeah, it's actually the same SDE in some kind of sense. And now we can define this discrete time approximation. If we let's start once again the discrete time approximation at u and at every time step we add in noise in now in the sense of the of the Wiener sheet, and we just freeze the coefficients in this SDE over the time intervals k over n to k plus 1 over n actually. So more or less standard discrete time approximation, at least if you consider it, for example, for ODEs. So this is the discrete time approximation, and the connection between this discrete time approximation and the different scheme we saw at the slide before the other slide is just that they have the same distribution as random elements of the continuous functions from R to R times n. So to understand how the different scheme actually converges in distribution to the values of the sigma CDF, it would be enough to understand somewhat quantitatively how near the discrete time approximation and the proper solution of the SDE were, because we already saw that the rescaled versions of this SDE converge to the sigma coalescing diffusion flow. So we can make some kind of diagonal argument, and the explicit form of the quantitative control we want to have maybe looks somewhat ugly, but let's see. When we now consider the solution of the SDE or the values at time n and the discrete time approximation as random elements of the continuous functions from a closed interval AB to R, then we have the following estimates on the expected difference in the subnorm. So it goes like 1 over square of n times some constants or exponentials of constants, and this constants roughly are the sizes of sigma and phi in some senses, and the sizes of sigma and its two derivatives are measured in the subnorm. So we already said we want them to be bounded, and because we don't do anything to the sigma in the convergence process, this doesn't really matter. But the sizes of phi and its two derivatives are measured in the L2 norm, and when we rescale phi to phi epsilon, we know that the L2 norm doesn't change, but the derivatives and the second derivative will get factors of 1 over epsilon to it. So the right-hand side will explode if we fix an n and let epsilon go to 0. So this is the first explanation of why n and epsilon n have to have a good ratio for convergence to hold. So some words on how to get such ugly estimates. So first, we can observe that if z and zn have a derivative with respect to the space variable, we can estimate the expected difference in the subnorm by estimating at one point and then integrating over an estimate of the derivatives at one point. So we actually just have to get pointwise estimates for that and its derivatives. And luckily we can do this because that and its discrete time actually discrete time approximation actually have a derivative with right to the space variable, which can shortly be seen if we just use the Kolmogorov continuity theorem to extend the difference quotients to 0. And for that, we have to get another estimate, which, yeah, it's not hard or anything, but you have to hold track of many things. So it's just a bit hard to write down. Okay. So now let's consider these pointwise estimates. I won't get into full detail, but just a few words on things that were used. So prominently, one will use the Ito isometry, or for P not 2, the Burkholder-Davis-Gundy inequality, to control the differences of these two martingales by the quadratic covariations or quadratic variations, I'm sorry, which are more easy to understand analytically, and then the Minkowski integral inequality to again exchange some expected values and integrals that will appear, and then use the Grünwald lemma, which is also used in getting such estimates between between a solution of an SDE and its discrete time approximation in the deterministic case, if you consider ODEs. So it's essentially the same approach with, but you have to do a little bit more on the stochastic side of things to get good control. And also, we can write down an explicit form, more or less explicit form of the derivative of Z, because it also fulfills an SDE. And explicitly, you can write it down as Dorian date exponential, like this. And having such an explicit form of it also helps in estimation. Okay, so just these few words on this. And now how to prove the approximation by a different scheme, by the above quantitative control between SDE and its discrete time approximations. So roughly the idea is just, we know the rescaled SDE solutions, they converge to the sigma CDF, and also the discrete time approximation is near the solution of n, at least if we would fix the epsilon n and have large n as the difference goes like 1 over square n. So but of course, for the diagonal convergence of the discrete time approximations to the sigma CDF, we have to control the second convergence, because as I already said, if we fix the n and now let the epsilon go to 0, we would not have that the solution of the SDE and the corresponding discrete time approximation are near. So that's the reason why the epsilon n has to go to 0 slowly enough, or to formulate it in another way, the relative rate of rescaling of the SDE and discretization of it has to be nice enough. So we cannot rescale too fast, and on the other hand, the discretization has to be fine enough in terms of the rate of rescaling. So, but if we have that, then we have diagonal convergence, and because the difference scheme and discrete time approximation have the same distribution, this also implies the convergence of the difference scheme in distribution. Yeah, So that was the last thing I wanted to say, actually, other than thanks for your attention and all the good questions. I really like that you asked so much.
Okay, thank you very much for the interesting talk. And maybe somebody have comments or questions, please.
May I ask a question?
Exactly.
Sure.
First of all, thanks for very interesting talk. And my question is regarding the approximation of the, say, Aratia flow with change in diffusion by a solution to the stochastic differential equation with interaction. I mean, that stochastic differential equation is with interaction. As I understand, you get that just only for fixed time, right? And probably you can extend this result when you fix a few times, right? And then consider the vector.
Probably, yes.
Didn't you get the result in the Skorokhod space where you initially considered your flow?
Yeah, I didn't try that, but I cannot think of an obvious obstruction, so this would probably hold if, yeah, I think it would probably hold, but I didn't try explicitly.
I also would like to pay your attention on one work. It is the work written by Victor Marx in Electronic Journal of Probability, where actually he does the same type, or like say the same type of the approximation of the modified massive Aratia flow, but there he consider a slightly different space. He consider L2 space on the set of parameters, but with values in the space of paths. And actually he proved the approximation in that space. Maybe the argument would be interesting for you if you decide also to work in this direction. And I believe that it would work also in your case, because your case is simple.
Yeah, that could probably be. I will look at it.
Mm-hmm.
Thank you.
Okay, thank you. And maybe some other questions, please.
Yes. Can I ask?
Yes, please, Oleg.
Hello, Yannick. Just to test the applicability of your method on existence and uniqueness. So what if you have an annihilating flow rather than coalescing flow?
What should the flow be?
Annihilating flow. So when two particles meet, they annihilate rather than coalesce.
Ah, yeah. So I didn't think about that either, but I think there's also more or less the same order structure on this problem. So one can probably use more or less the same arguments. I will not speculate more than that, but yeah, there's the same order structure, which so the non-crossing, which really helped here. So maybe one can more or less do the same thing.
I suppose the main difference is that you cannot build the process by adding coalescing paths one by one. Annihilating paths, yes.
Maybe.
Yeah. Okay, thanks.
Okay, thank you. Other comments, please? I also want to ask you a question about the diffusion coefficient sigma. As I understood, it can be, for example, equal to 0 in some points, yes?
Yeah, so the coalescing diffusion flows I mentioned here aren't coalescing for all sigma here.
Okay, it means that the image of the real line at the positive time t under flow is not already just a locally finite set of points as it was in Aratia case. And from this point of view, it is interesting what kind of measures you can get from the Lebesgue measure for different sigma, how it depends on sigma. Yeah. maybe you can get very ugly measures, like something concentrated on counter set or something. Yeah.
Yeah, I think there is already a little bit of work on that. I think in some article of Harris, he also discusses something like this, or at least conditions when
You know, of
it's not
course,
actually exactly this. So yeah.
we can
Maybe.
prove, I think, that if sigma is strictly positive, because it continues, then I think that in this case we can prove that everything will be similar, like in Ratia case, and the set, the image will be locally finite set. But if sigma allows to be 0 somewhere, then at least it is interesting to analyze what can happen.
Yeah, but do you really think it would hold for every strictly positive sigma? Maybe there could be a problem if it isn't bounded by below, say by
You see,
epsilon.
it is not necessary to suppose it is bounded, because if it is strictly positive, so then on the finite intervals it is already bounded, separated from 0, and it's enough. Yeah. So
may also maybe it is also some question, or also would like to pay your attention. I remember that Georgy Ryabov has some general construction of stochastic flow, and also there is a paper of James Bell, a student of James Norris, who also construct the stochastic, like stochastic flows, and he considers a backward stochastic flow. So did you check that work, whether, say, the existence of the flow which you considered cannot be obtained from that works immediately?
No, no, that work I didn't check. I checked a few works, but the works I checked didn't really focus on regularity of the flows, but more on the on co-cycle properties and things like that, which are relevant. Yeah.
But as far as I remember, the work of Bell is related to the flows on a circle, right?
All right, right. But still, I mean, okay, it is not a very big difference, and so on. So you know.
Yeah, but it's technically it's.
If he considered back maybe dual flow, not backward, yeah.
Dual.
Dual flow. So in this case,
the question of existence should be discussed. It is only the question whether, I mean, you can do that simpler.
Okay.
As I understand the work of Yannic,
let's
it is not actually the construction. It is more like the approximation and so on and so forth. So probably also it would be interesting or important to compare one work with another.
Let's see. Okay, thank you. Yannic, thank you again for interesting talk. For today we finish our work, and maybe Georgy knows the name of the next speaker.
Yes, it will be Nasir Ganihadjaev.
Very good. So see you next week. Bye.